Okay, so again this is about a reflection at spherical surface. So this could be a meter, okay, which we called convex meter. So light originated at some source. This is the source of light, and light ray hits the meter. So we can have trillions of light rays here, but out of those trillions of light rays, we'll only consider two light rays. One is this one, and the one that hits at the center. Okay, and the light that hits that point M, that goes through point P, because the light will be reflected back, and the reflected light goes through point P. Okay, and this R is the center of the sphere. If you consider this to be a part of a sphere, okay, because we are considering a spherical surface, so this is a part of a sphere. That's not perfectly spherical, but this R would be the center, and this distance would be the radius of that sphere, which is called the radius of curvature. Okay, and here S naught is the object distance between the object and the center of the meter, and it goes through P. So the image of this source or object is formed at P. So SI is the distance between the image and the center of meter, so it's called image distance, and theta I is the angle of incidence. So this light hits this meter, part of this meter, at this angle, theta I. Okay, if you draw a tangent line, this would be normal or perpendicular to that tangent line. So this angle is with respect to that normal, and this would be a reflected light or reflected angle. So we can call that theta R, and theta R would also be equal to theta I from the law of reflection. Okay, so let's consider this triangle. Okay, this is some general triangle. In this triangle, side A, B, and C are opposite to this angle, theta A, theta B, and theta C. And you might have seen this in trigonometry, which is called law of sines, which is so sine angle over its opposite side is equal to sine of other angle over opposite of that is equal to sine of the third angle over the third side. So that's law of sines. This is true for any triangle. Okay, now in this case we'll be using this for, okay, that's the law of sine. We'll be using this for this triangle, okay, SRM. SRM, so that triangle. So in this triangle, sine theta I over opposite of that is SR, okay, which is this whole distance minus this R. This is R. So that whole minus R is this distance, okay, that side, which is opposite to that. So S naught minus R, and then sine theta 1, sine of that, and opposite of that is this distance, which is R. That's the radius of the sphere. Okay, so that's for that triangle, and we can also use that sine law for this triangle RPM. RPM is this small triangle. That triangle. So for that triangle, sine theta I, so this is sine theta I again because these two are equal, over this side, which is this whole thing minus that. Okay, so this whole thing is r, and that is SI, image distance, that is equal to that. So that's that side, and then this is theta 2. Okay, so this angle would be 180 degrees minus theta 2. So sine of that angle over this side, which is r. Okay, so we are considering only 2 sine angles. We don't need to worry about all 3. Okay, this is true for all 3 angles, but we are only considering 2 angles. So those are the sine laws for these triangles. Now we can divide this by that. Okay, so this is basically sine 180 minus theta is sine theta 2 over r. Okay, now if I divide this one by this one, then I will get sine theta over this r and r will cancel. So sine theta 1 over sine theta 2, which is that, is equal to this sine theta I and sine theta I will cancel. So I'll have this one on the top and that one on the bottom. Okay, so that's from the division of 1 over 2. Okay, now one thing here we will do is something called paraxial approximation. Paraxial approximation is when this angle is very, very small. Okay, so in our previous treatment we didn't use this approximation, but here we will say the angles are very small. When the angles are small, we can approximate for a small angle. Tan theta is equal to sine theta is equal to theta. Okay, so here if we consider theta I, then theta I would be this height. Okay, that's the height over S naught. Okay, so this distance, we consider that this to be pretty close to the center, so we'll neglect this distance. So we'll just say theta 1 is height over S naught. Okay, opposite over adjacent. Similarly, theta 2 would be h over Si. Okay, considering this is a small distance. So actually this is tan theta, but because it's small angle, so we can use this small angle approximation. So we can just write tan theta is theta. Okay, and we have this equation from previous slide. So that's our equation. So we use small angle approximation. So if we use small angle approximation, we can write sine theta as theta 1, sine theta 2 as theta 2. Okay, that's what we have here. So I'm writing theta 1 and theta 2, and then replace theta 1 by that and theta 2 by that. When you replace that, h and h will cancel, and then you will have Si on the top and S naught on the bottom. So this will go on the top. Okay, so here you will have h over S naught, h over Si. So h and h cancel. So you have Si, S naught, and the right side is as it is. So I can now rearrange this. Okay, so multiply, cross multiply that, and then rearrange, you get this equation. Okay, that's just the algebra. And we can define the focal length as r over 2. Okay, r is the radius of curvature, radius of this circle, this sphere, and we define focal length as half of that. Okay, so this distance is focal length. If we use that, then we'll get this equation. Okay, this is called meter equation. Okay, so we'll be using that for our problems. So that's the focal length, and we already talked about that last time. So if you hit the rays coming from infinity far object on a concave surface, then the rays will pass through a focus. Okay, this is focus or focal point. And if the rays hit on this convex surface, this is convex, this is called concave, this surface, then the rays would be diverged. So you see here the rays are diverged. They are diverged in such a way that they appear to be coming from this point, okay, this virtual point. And you can also do the time reversal here. So if you, instead of passing the light straight like that, if you pass along this deviated direction, then these light rays would go through the hit the mirror and go straight, okay, parallel to each other. Okay, so the next thing is, so we just saw the reflection. So this is the reflection. Now we want to talk about refraction. Okay, refraction is bending of light, and here we are talking about spherical surface again. Spherical surface that separates one medium to the next medium. So we have a medium here. This could be air. Okay, it doesn't need to be air, but it could be air or water, and this could be glass. Okay, so we have two medium, and the two media are separated by this boundary, spherical boundary. So this one has refractive index Nm, this one has refractive index Nl. So just like before, we can use sine law of sines. So we will be using that in this case also. Okay, so let's see that here. So this is for this triangle. This triangle. Okay, so sine 180 minus theta I. So this is sine 180 minus theta I, because this is theta I. This is straight line, so this would be 180 minus theta I, and opposite of that is this side. Okay, this side. So you have this source here. This source goes straight through the center, whereas when it hits this part, it will be bent. Okay, it will be refracted. So instead of going straight like that, because of the change in medium, so it goes bent. It goes through that direction, and that's the point where it focus. So that's that angle. That opposite of that is that which is this distance plus this distance. Okay, so that's S naught, and this distance is the R. Okay, so this C is center of curvature. So if you make a sphere here, this would be your center. So that's R. Okay, so this is R, and that's S naught. So total is S naught plus R, and then we can take another angle here. So this angle, so sine of that angle, and opposite of that is this side, which is the radius of this sphere. Okay, R, which is also called radius of curvature. So that's that, and then sine 180 minus theta I is sine theta I. Okay, that's that, and that's just as it is. So we have this expression. In similar way, we can use another triangle. So this is this triangle. Okay, so sine theta T, this is the angle of refraction or transmitted angle. Sine of that angle over opposite of that is this side, and this side is this whole distance minus this distance. This whole distance is SI. Okay, here is the image. So image distance minus the radius of curvature R. And then let's consider this angle theta 2. Sine of that over opposite is R here. That's R. Okay, you get that. So we have two expressions. One is this one, and the other one is this one. So divide the two expressions. By dividing, you get this expression, Okay, you're just dividing the previous one with this one, and then we can use the Snell's law. So Snell's law is NL sine, so NL is that sine of theta in this side, the angle is T, and on this side refractive index is Nm, and the angle is theta I. Okay. The angle at which the ray hits on this side is theta I, and the angle at which the ray hits or emerges on this side is theta T. So that's what we have. So sine theta I over sine theta T is that, just using that. Okay. Now, just like before, we can use small angular approximation, which we call paraxial approximation. So paraxial approximation gives us that to be theta 1 over theta 2. Okay. And then just like before, we can use tan theta 1 is equal to height over that S naught, and tan theta 2 using this triangle tan theta 2 would be height over that distance, which is image distance. Okay. So this one is from this triangle. Okay. So this is small angular approximation theta 1, theta 1. So the ratio of theta 1 and theta 2 would be h over s naught, h over si, and h will cancel, so that will be the result. Okay. So we have used small angular approximation. So that's our result. Now you can rearrange the things here. So we have this expression that is equal to that, and you do the cross multiplication, cross multiplying, and do a little bit of algebra, you get this expression. Okay, that's pretty straightforward, not that difficult. So basically Si minus R NL S naught is equal to S naught plus R in Nm Si. So multiply term by term, and then divide by both sides by the common terms, you get that expression. Okay. And now if we consider this kind of lens that has two surfaces, okay, two refracting surfaces. So here we only have one refracting surface, but in normal lens we have two refracting surfaces. So one is this refracting surface and the other one is this refracting surface. So for the first refracting surface, okay, we have this equation, same equation here, just like here we have this refracting surface. We have this refracting surface here. So for that, that's the equation. So this is the refractive index of the first medium, Nm, and this is the refractive index of second medium, Nl. Okay. And this is object distance, image distance, refractive index of first medium, refractive index of second medium, and radius of curvature. Okay, this is exactly the same equation that we got here, nothing different. But for the second surface, the image formed by this one would be now the object for the second surface. So this is the distance at which the image is formed. So image, if you just consider this surface, it will form the image at this point. Okay. So then this distance would be the object distance for the second lens or second surface, and this distance is d minus si. Actually it's si minus d, but we would be writing d minus si because this would be negative of that, and this negative tells us that it's virtual. Okay. So we will write the distance in general as this one. And if you have a negative here, that means it's a virtual object. Okay. So because this d is smaller than s, this distance, so this would be negative. Okay, and that negative implies that it's not actual object, it's just the virtual object. Okay, and it's a virtual object, so your ray is still in this medium. Okay, you got the ray from the refraction of this ray through that, so it's still in this medium. So your first medium is NL, and when it comes out in this medium, your medium would be NM. Okay, and that's the image distance. So this is object distance. In this case, it's virtual object, and it's image distance. Okay, so NM minus NL. Okay, second medium minus first medium over radius of curvature. Radius of curvature is for this sphere, that r is the radius of curvature. This is for the second surface, that's for the first surface. So we have two equations for two surfaces, and we can subtract the two equations. Okay, so when we subtract this one from this one, we get this expression. Let's see if it is subtracting, or let me clear everything. So we are combining these two equations to get that. So NMSOI, NMSOI, NMS1, that's that. Okay. Okay, seems like we are adding, not subtracting. So because we are adding these two, okay, and then NL, NM. Okay, so it involves a little bit of algebra here. I don't want to spend too much time on this one because that's not very important. Okay, maybe I can show this next time, but I just want to show you the result. Okay, it's not difficult to get this one. I just need to do a couple more extra steps here. But we know that this comes from the combination of these two. Okay, there's no complicated math involved here. Oh, actually, it's adding. Okay, so I don't know why that is. So by adding these two, you get that, and then rearranging the terms. Okay. So then you have this equation. Okay, that's just same as the previous one. I just repeated that, and then by using the small angle approximation or thin lens approximation, we can consider that this d is really small. Okay, so in this picture, this d is really small. That's why we call it thin lens. Okay, so considering it's a thin lens, we can neglect this d. This d could be neglected. Okay, if we do that, then we get this equation. Okay, so basically this n is ratio of two refractive indices, NL over NM. Okay, so you divide both sides by NM, NM, NM. So you get this and this cancel, so that you have that, and then NM over N. Yeah, so that and that also cancel, so that you have 1 over SI, and then NL over NM is N. Okay, that's that, and then NM over NM is 1, and then that is as it is. Okay, so this equation is called Lens-Maker equation. One more step, and then we also know that we also know that when we place an object at infinity, when S naught is at infinity, the image is formed at focal length. Okay, SI would be at focal length. So that means when object is at infinity, this would be 0. Okay, 1 over S naught would be 0. So that goes to 0, and then this would be 1 over F. Okay, because whenever S object is at infinity, image is formed at focal point. That's the object distance, image distance, and this right side is as it is. Okay. So if I substitute this thing by 1 over F, then I get this expression. Okay, exactly same as the one we got in the meter. Okay, this is here. This is called thin lens equation, and this equation is called Lensmaker equation. Lensmaker. We'll be using both of these equations. Okay, and this is what I wanted to get to do the questions, to solve the problems. Okay. So we have 10 minutes. Let's look at number 3. So let's go to number 3. I will give you a hint and you can do that. So you have a convex lens. Okay, that's the convex lens, and its focal length is 25 centimeters, and its refractive index is 1.5, and it is immersed in water. Okay, that has the refractive index of 1.33. So as a consequence, there would be different focal length. Okay, so this is when it's in air. Okay, but when you immerse this in water, it will have different focal length. Let's call that F prime, and we want to know what that is. Okay, so we'll be using Lensmaker formula for solving this. So the clue here is we have this Lensmaker formula: 1 over F is equal to n minus 1 over 1 over R1 plus 1 over R2. Okay, so we have two curvatures here, this one and this one. I will write separately. Okay, so this is R1 and this is R2. Okay, so that's that. This is the radius of curvature, because this is made up of two spheres, one on this side and the other one on this side. Usually they have same curvature, but sometimes they may be different. So that's that. So this is, let's say, for air. Okay, now for a water interface, let's call this F prime, n minus 1, let's call this n1, 1 over, so this won't change. Okay, R1 over R2, this 1 over R1 and R2, because it's the same material, so that doesn't change. What changes is this n1 and n2. Now we define n1 and n2. If you remember, n is refractive index, so look at the PowerPoint here. Here, NL over NM. Okay, refractive index of the medium over refractive index of the surrounding medium. In refractive index of the medium, here is the refractive index of lens, and refractive index of surrounding medium, which is, in this case, in case of water it's W. In case of, no, that's air, N1. So this one is basically n1 is 1.5 over 1 because it's air, and n2 nl is 1.5 and nw is 1.33. Okay, so you need to plug that here and then divide the two equations. So you'll get 1 over f (25). So that's 1.5 minus 1, and then that's as it is. Actually this is 1, actually this is minus probably. Let's see, maybe I forgot. Yeah, so that's minus. So this is r1, 1 over r1 minus 1 over r2. Okay, so make the change there. And then for the second one, we have 1 over f prime is 1.5 over 1.33 minus 1 over r1 minus 1 over r2. So divide the two equations, they will cancel, and then find f prime from that. That should be pretty straightforward. I think you can do that. Just the basic math, right? All the numbers are there. You just need to find f prime.
Yeah, like 96. Okay, I got 97.
97. Okay, it's about 97. That's fine. I don't have answer.
I was like, that's a large error.
Yeah.
Right in that. But okay, that's fine. Okay. Yeah, I was like, I'm not gonna say nothing. There's a lot larger. There's only two of us. Yeah. We get two different answers, and we're like, well, which one of us messed up?
But one is 96 and one other one is 97, right?
Yeah.
So they are pretty close.
It's probably how we rounded the.
Yeah.
I didn't round. I did.
Okay. So let's look at number 6. I mean, number 6 is also application of this Lenz-Macquer formula. So this is pretty straightforward. So first thing you can do is find f, and then find the so first you use this equation, and then use this equation. Okay, so this equation will give you f, and then use that f here, and then the object distance is also given, and using that you find SI.
Does it matter which radii we use for 100 and which one we use for 20? Should we do the 100 first as R1?
Usually the front one, this one would be R1, and this one would be R2. So is it?
It just says a thin
Yeah, so let's use the first one.
Is it supposed to be a positive or a negative number?
This is convex lens. It's supposed to be positive. So to get positive, yeah, that's a good question. To get positive, we need to use the smaller one in the front. Yeah.
I got negative using the bigger one.
Yeah. So
So the bigger one is always the back. Well, the biggest R would be the smaller number. Yeah.
right.
Basically, get a positive number. Yeah.
But for diverging lens, concave lens, it will be negative. So that's something you need to keep in mind. Yeah. And then this question is also asking for magnification. So magnification is given by this formula. You might have seen this in introductory physics. So it's image distance over object distance. Okay. So you will get image distance from here, and then just take the ratio of that to get magnification. And ray diagram, so try that ray diagram. You might have done this in introductory physics. If not, we will do that next time. When are we doing the test? Did we decide to do the test during the lab time or class time?
Doesn't matter to me.
Okay, maybe we can use the lab time for the exam, and then we can do some practice during the class time. But Thursday, kid, you won't be here, right? During the lab time.
Yeah. One of my other classes was only 12 weeks.
Okay.
And it was the one that I couldn't do Thursday labs for. But
Okay.
now that it's over,
So maybe, yeah, we can complete this during the class time and do a little bit more questions also more, and then just take the test during the lab time. And then you can come on Friday to finish your lab.
yes.
That lab, yeah. So, yeah, if you want to, yeah, do number 7. 7 is also pretty straightforward. It should just take a minute to do that. So it's asking for radius of curvature. You have to find r in this case. So here, this one is the plano-convex. Plano-convex is something like this. One side is plane, other side is like that. So for plano-convex lens, this radius of the plane surface would be infinity. Okay, so your formula is 1 over f is equal to 1 over n minus 1. So whenever this is in air, you can just use the actual refractive index here. But if it is not in air, then you will need to use the ratio. Okay, so this ratio needs to be used when you are dealing with two different medium that are not air. And so 1 over r1 minus 1 over r2. So in this case, the focal length is 25 centimeters. Refractive index is 1.52, and then this r2 is infinity, and then you can find r1. Okay. So I would, yeah, complete 3, 6, and 7, and then we will do the rest next time. Okay.